in higher academic grade. And to his credit, he has been honored by, he is the editor-in-chief, associate editor, Frontiers in Computational Neuroscience in 2021, associate editor, Advances in Difference Equations, Springer Nature, USA in 2019. And he was also visiting scientist in the University of Le Havre, Normandy, France in 2018. And he has guided close to, I think, 14 research theses he supervised. And he is member of many professional bodies, including American Mathematical Society, International Academy of Ecology and Environmental Science, Hong Kong. He is a board member. International Society of Computational Ecology, Hong Kong. There also he is a board member. And members of various government committees, including member Program Advisory Committee of BST SAR. Then he chaired GATE JAM for 2020 and 2019. And he completed successfully 7 research projects funded by government agencies. And he published more than 178 research articles in various journals of repute. With these words, I welcome Professor Upadhyay, and I'm really thankful that he could spare some time from his busy schedule to interact with us. I hope all the participants will be benefited, and I urge all the participants to actively participate, and whatever doubts they have, they can put up, and we can discuss at the end. With these words, welcome, sir. You can go ahead with the presentation.
Okay. Thank you, Professor Jamal. I am visible to all of you and audible also?
Yes, yes, very much, yes.
Oh, okay, okay. So, good morning, everyone. I hope this 6 days interaction has been enriching for all the participants. And the topic of this International Faculty Development Program is quite intriguing to me. And today I will talk about the modeling virus dynamics in space and time, review of the SIR epidemic models. Let me first thank the organizer for inviting me for this talk. And I appreciate the initiative taken by Professor Jaydev Chattopadhyay and Professor Jamal for organizing this event and inviting the distinguished expert in the field like Professor Martecheva, Professor I.M. Elmojtava to share with us their invaluable knowledge and experience. This will surely inspire the young generation, young researcher working in this area. I also want to extend my gratitude to Professor Jay Prakash Singh, HOD of Department Mathematics and Computing, and Professor K.R.S.S. Rao, the Honorable Vice Chancellor of the University, for bringing together this virtual IFDP program and making this event a great success. I also wish for the success of this event. So let me come to the topic with these words. As you all know, recently the world has experienced the emergence of major devastating epidemic outbreaks and the spread of the COVID-19. So, understanding the modeling of virus dynamics of infectious diseases hold the key for designing control strategy from the public health perspectives. And the temporal and spatial dynamics can be essentially different, and while its results may be misleading in some situations, temporal analysis provides an important direction for understanding the spatial or spatio-temporal dynamics. So let me first introduce you with the virus. What is virus? As you all know, this virus is an infectious microbes consisting of nucleic acid and surrounded by the protein coat. So we call it the nucleoprotein. Nucleoprotein means nucleic acid with protein. That is nucleoprotein. It has many characteristics. It contains the infectious genetic material. It is either RNA or DNA, not both. And it has many viral capsid complex structure. So these are the some facts about the virus dynamics. Before modeling, we need all these things. So it covers the coat of the protein and most abundant biological form of life on the planet. But it cannot be cured, but vaccination can prevent their spread of the virus. Let me show you some virus, well-known viruses like influenza virus. How to remove this one? Let me remove this disturbing. Okay, so these are the few pictures of the structure of the viruses, like influenza virus, Ebola virus, this is Zika virus, and this is the coronavirus, and this is the HIV virus. All this virus looks very interesting, the structure. Now let me show you the how the body fights with the viruses. The body breaks down the viral genetic material, RNA or DNA, through the process, and that process is called RNA interference. And the immune system produces the antibodies that bind to viruses to make them non-infectious. And the T cell sent to destroy these viruses. And these are the way how the viruses spread. So these are some mechanism. The viron enters into the cell and it becomes virus. The virus reproduces, creating the viral protein and genetic material, okay, instead of the usual cellular product. Then virus insert into the genetic material into host and take over the cell's operations. And these are the different way of spreading the virus, just by touching the hands and exchange of salvia, coughing, sneezing, sexual contact, and contaminated food or water. So this way it will spread rapidly. With this introduction, let me outline my talk. So I will first introduce you how the motivation about this work. Then I will review the whole modeling process, specifically the SIR epidemic model. And the basic understanding is this. We have the basic principle, the old model, new application. Just like we have the old medicine, new usage. So on this basis, SIR type model is one of the basic model which started with its pioneer worker Carmack and McKendrick in 1927. So these are the basic model for modeling most of the epidemics. That's why we will review different scientists work with the different form of the SIR model. So we discuss full detail. We will discuss here how to solve analytically, how to solve numerically, all this way of with the SIR model. Then we will develop some non-local epidemic models. Then we go for the age structure and multiple group modeling. And then with the model with comorbidity. And after that, we will go the vaccination strategy in the age structured model. We will also show you the qualitative dynamics and quantitative analysis. In qualitative dynamics, I will show you the how to calculate the basic reproduction number, its importance, all these things, stability, behavior. Then in quantitative, how to fit the real data in the curve fitting, how to perform the sensitivity analysis, bifurcation analysis, what is the role of force of infection and its effect, entropy within the force of infection. Then we go for the optimal control strategy. Then finally the conclusion and discussion. I will also show you the important questions for which we cannot have the model till now. Then I will give you the final message regarding to that. So let us start with the motivation part. So let me show in the PowerPoint presentation mode. So as we all know, emerging and re-emerging the infectious diseases are the big challenge in the public health, agriculture, as well as the wild management. And recently we have seen many virus diseases have occurred, like SARS-CoV-2, Ebola, Zika, all these things. And these are the challenging topic for the scientists working in this mathematical epidemiological, how to model the scenario, how to draw the conclusion, and based on our conclusion, government will formulate the policy to control that disease, all these things. So we are mainly interested in these questions. First, the time period between one gets infected and passes the infection to the next person. What is the time period for that? Next question, how can the spread disease will be reduced or stopped? And thirdly, how to control the disease or infection. In this modeling scenario, one of the important word appears, that is the incubation period. So people should know what is actual incubation period is. So it is the interval between the effective exposure of susceptible host to an infectious agent and the appearance of the sign and clinical symptom of the disease in that host. And during that period, the viral genome will replicate and host responds to producing the interferon, leading to the classical systems of the infections like fever, pain, nausea, all these things. And one of the example is during the incubation period, the Ebola infected patients, they do not pass the virus to the other. This is the speciality of the Ebola virus. And here you see how it came from the wildlife to the human population. So this cartoon was presented by CDC, and here we will see that it gives the information: human or animal invasion of new ecosystem, climate changes, increased international travel, and environmental degradation provide the opportunity for existing disease to spread and new infectious disease to form. And the data shows that with the up to today's studies, it shows that 60% of the emerging infections in the human originated from the wildlife. And therefore, it is important to study how the infections spread in wildlife community and how they are transmitting to human populations. And this is the dangerous situation. Later stage, it becomes human to human transmission. So the conservation biologists also interested in answering the question how the parasites affect the biodiversity and ecosystem dynamics, as infectious diseases can be a factor regulating the host population. So for modeling point of view, modeling can help in identifying the trend, making forecast, and optimizing the various detection, prevention, therapy, and control program. So understanding the transmission dynamic of infectious disease in community, region, and country, it will help in designing the control program by the government for these diseases. So let us come to because this is the development program. So let me start with the basic terminology, what we are using in the epidemiology. So generally we take in the beginning the susceptible population as a total population. We assume that in the beginning there is no disease invaded the system. So total population is taken as ST equal to N, and that is constant. This is the complete susceptible population. So these are the terminology used for modeling: susceptible population, exposed population, infected population, and recovered population. Apart from these, people are also using quarantine population, isolation population, all these things. Frequently, they used all these things. Now, the diseases are of the mainly three categories. It is divided into three categories: endemic disease, epidemic disease, and the pandemic disease. Endemic disease, it is the constant presence of disease or infectious agent within the given geographical area or given population. For example, let us take chicken pox, cholera, typhoids. All these are categorized into the endemic disease. Epidemic disease, what is the epidemic disease? It is the sudden outbreak of the disease that is spread rapidly among the many population, many people in the community at the same time. That type of disease is called epidemic diseases. And if this outbreak is spread across the continent, then it is called the pandemic disease, as we have seen in the case of the coronavirus. So what are the major differences? The epidemic disease are used to describe rapid outbreak, and that occurs in less than a year. But endemic disease are used to study disease over longer period, during which there is a renewable of susceptible population by birth or by recovery from the temporal immunity. So based on this idea, we categorize the disease into different categories, and we use the hypothesis and modeling procedure for modeling that disease. There are some more important terminologies are like basic reproduction number, contact number, and replacement number. I think everybody knows all these things. And there is a relation between these three. R naught is greater than equal to sigma. Sigma is contact number, is greater than equal to the replacement number. And this greater than equal to becomes equality at the time of invasion. And when R naught equal to this sigma, this is for most model it happens, and sigma is greater than the replacement number after the invasion for all the models. So this terminology we will use. So let us take what is the role of social distancing. In the corona period, we have seen government issuing the guidelines, so we should have to maintain the social distancing. So how it is incorporated in the modeling scenario. So let us take what the social distancing do. It measures the social distancing by decreasing R naught, and the exponential growth model changes into the exponential decay model. How it happens? Let us take the rate of change of the infected population. So di by dt equal to R naught into I. So just to divide by I, so di by I equal to R naught into dt. If you just integrate this, you will get this expression. IT, the total number of infected population, is initially infected population into e to the power R naught minus 1 into t. So if R naught is greater than 1, this is the exponentially growing. And so we have the guidelines. So we try to maintain the R naught less than 1, so that it becomes the taking the trend of decaying. So social distancing, if you increase if you maintain it less than 1, it is the healthy situation. The disease will not spread exponentially. So this is the relation between the social distancing and R naught. So the epidemic models are used to describe the rapid outbreak that occur less than 1 year. So another terminology is incidence function, FSI. For modeling, this is very important. So it is a function from R2 to R, and it is a continuously differentiable function, and satisfying these three property: F0I equal to Fs0 equal to 0, it is a strictly monotonic increasing function for s greater than equal to 0 for fixed I, and monotonically increasing function for I greater than equal to 0 for fixed s, and phi si equal to fsi by I. It is a bounded monotonic decreasing function for I greater than 0 and fixed s greater than 0. And third property is this one. So incidence has many categories. You will find it horizontal incidence, standard incidence, even the vertical incidence, and corresponding transmission is called horizontal transmission, vertical transmission, and standard transmission, all these things. And they can be modeled with these terms. If you take the bilinear incidence or the density dependent transmission, we frequently use this term, beta Si. And if you take the standard or frequency dependent transmission, we will divide it by capital and total population. And if you take the saturated incidence rate, we will take either this or this type of function. So let me give you the brief review of the non-linear incidence function taken by different people, and it is a chronological order. Let us York and London has taken this type of non-linear incidence function in 1973. Capasso and Serio, they have taken this type of and seen the effect. May and Anderson has taken this type of function. Ruan and Wang, they have taken this type of function. May and Anderson, they are also the pioneer worker in this field. They have taken this type of function. So these are the few forms of the non-linear incidence function frequently used by different people working in this area. So let me go to the model. What different type of model in the epidemiology exist, or we can model this scenario. We can model for transmission or spread dynamics. We can model for the control dynamics. So the model is called control dynamics model. We can also model for survival dynamics, and that type of model is called survival dynamics model. We can model for relapses, and all these things I have recently combined all these things for different scenario in my recent book on the spatial dynamics and pattern formation in biological population. So here we have discussed all the Ebola virus, Zika virus, and the general epidemiological modeling. Even the last chapter is related with the neural modeling, brain dynamics, and the disease appears in that one. And previously in 2013, I also wrote another book based on the mathematical modeling and chaotic dynamics. So these two books will help the younger generation for modeling the scenario. Let me go with the reviewing the all SIR model. The story starts in the 1927 when the Kermack and McKendrick wrote a very nice paper, a contribution to the mathematical theory of epidemics, and that published in Proceedings of Royal Society London 3A. And that model was basically the variable infectivity model. In that model, they have considered the infection rate depends on the duration of infected and infectious status. And the infection occurs only once in the lifetime of the particular individuals. So these are the people who did this one. And what is the importance of that model? So the importance of that model is it can model the epidemics with long incubation period. And we have seen what is incubation period. And here the variable infectivity, and that is used in the HIV and AIDS epidemics. So that is the specialty and importance of that model. Later on, they have also developed the more complex epidemic model in these two papers. And the model developed in this paper in 1933, they are the variable susceptibility model. And in that model, the transmission rate depends on both the durations of the infected host and the susceptible host. And they applied the epidemic that are appearing due to the genetic changes of the virus. During that time, they have not thought that, but they have the scope to incorporate the genetic changes. And we have seen in the report in case of coronavirus, it is frequently changing the gene. So this model is best suitable for coronavirus modeling also. And many people have used that one. And in that case, the vaccination cannot control the diseases. In all these cases, we can use the variable susceptibility model. So, this is the deterministic structure model for modeling the spread of the infectious diseases. The basic form is this, as ds by dt. If you take the variable infectivity model, it simply becomes the OD model, simple OD model. And that OD model is ds by dt equal to minus beta si, di by dt equal to this, where beta and gamma lie between 0 and 1, and rate of change of recovered population is gamma into y. So if you add all these things, right hand side, it becomes 0. So this population S plus I plus R becomes constant, where this beta is the transmission rate, gamma is the mean recovery rate, it goes here, and 1 by gamma is called mean infectious period. And they have nicely used that outcome of that model for the data for the Bombay plague in 1905 to December 1905 to July 1906 data. And this, on the ordinate, they have put the number of the dead per week, and on the abscissa they have taken the time in a week, and they have, and the data is nicely fitting in that one. So they have given only this figure in that proper original manuscript. So, and if you analyze this model, you will find how to find the basic reproduction number. Just to take common I, you will get this bs by gamma, and the fate of the evolution of the disease depends on it. And if you take I dash less than 0, this implies effective reproduction number RE should be less than 0, and which implies that the infected population I will decrease and decrease monotonically to 0. If you take rate of change is positive, this gives you effective reproduction number is also positive, and it will increase, and therefore the effective reproductive rate acts as the threshold value that determines whether the infectious diseases will die out quickly or it leads to the epidemic diseases or later on pandemic diseases. So it depends upon the effective reproduction number. Let us go to the analyzing the model more in that. So in the start of the epidemic, when the effective reproduction number is greater than 1, we assume susceptible population is 1. Then di by dt becomes beta, s is 1. We take common I, beta minus gamma it. The infected population I is initially increasing exponentially according to this rule, and the infected population will reach to the peak if di by dt equal to 0, and it will occur n when the effective reproduction number is equal to 1. And after the peak, the infected will start decreasing exponentially, and it follows this way, and eventually the system will approach to 0, and S approach to 0 and I approach 0. So interestingly, this existence of threshold for infection is not obvious from the recorded data. If you record the data, this will be not an obvious phenomena. So however, we can discern this from this model, and this is the crucial in identifying the second wave. We have seen in coronavirus, we have second wave, third wave, all these things. So this we can use for identifying the second wave. So in the original Kermack and McKendrick model, they tried to solve it analytically. So what they did, I just want to present their work. So they have taken dr by dt equal to gamma into I. I is what? S plus R plus I equal to n. So I is replaced by n minus S minus R. And if you divide ds by dr, it will give you minus beta by gamma s. And if you simply integrate it, it will give you s equal to s naught e to the power minus beta R by gamma. We replace this value of s in this gamma into n minus s minus r. So this becomes dr by dt equal to gamma n minus s naught e to the power minus beta R by gamma minus R. And if you expand this exponential term in the power of beta r by gamma and take beta r by gamma is very, very less than 1. So this dr by dt becomes gamma into n minus e to power, this is 1 minus this. So this will give you this. And we consider up to the second term s naught beta square r square by 2 gamma square. And if you take n minus s naught equal to I naught, and I naught we assume in the beginning it is small, and beta r by gamma is less than 1. So we also consider this third term. And if you solve, this is the non-linear equation. If you solve by doing some algebra, you will get, this is the solution of r. R equal to gamma square by beta square s naught into this term, where this term phi is given by this, and under root minus q is given by this one. And if you take s equal to gamma, s naught equal to this gamma by beta, this indicates that no epidemic will take place. And at the end of the epidemic, r will be this value, r equal to 2 gamma by beta s naught into this one. And this in 2014, the Professor Harko, he gave the exact analytical solution of this SIR model. And this is the model. What is his approach? Let me show for the younger generation how to get the. So as you all know, the exact solution is the best solution. So first we should try for that one. If it is not possible, then we go for the numerical solution and other solution. So here people have tried their own way to get the exact solution. So this is the actual model and with initial condition. And what he did, he just divided s dash by s equal to minus beta I, and differentiating this with respect to t, he got the, you just divide by beta, s dash by s whole square minus s double dash by s. This becomes di by dt. From here you first find I equal to minus 1 by beta s dash by s. Just differentiate both sides, you will get this one. And use this in the second equation here, di by dt equal to this. So you will get this one, equation number 1. And from the first and third, this and this, we will get dr by dt equal to this one. So this will give you s, value of s. We have also got previously in the Karmak mechanic work. So s naught is comes out to be this. And now you consider s dash equal to, from here, k minus k beta by gamma into r dash of this. From here we can take from this equation. And after differentiating this, we will get r double dash is this one. And by just substituting the expression 1 to 3 into 4, we will get r double dash this, where just you take the different variable ut is e to power minus beta r by gamma as a variable transformation, and you will get this equation. This equation, second order differential equation, converted into in the new variable u as this, and the initial condition in this term will be this. And if you further take the variable transformation phi as dt by du, so this equation gives you the Bernoulli type of equation, and we know how to find the general solution for the Bernoulli equation. And so this is the general solution of the Bernoulli equation. That will give you dt equal to phi of du. From there we can find the time t in the integral representation, and t naught is the arbitrary integral constant. And if you take in the beginning t naught equal to 0, this will give you the analytical solution, exact solution of the Karmak mechanic model. And in the given parametric form, where parameter s is k into s in terms of parameter is k into u, and just you get du by dt in this form, and you will get u equal to this. This will give you r. We put r in the given equation, and here you will get the complete solution of the analytical solution of the SIR model. Many people have used the numerical method for finding this. So some well-known numerical methods are a domain decomposition method used by Bijare in 2006, variational iteration method in 2007 by Raffi et al., homotopy perturbation method in 2007 itself by same group, and differential transformation method by Batiha in 2011. So these are people have tried to find numerical solution of the SIR model, well-known SIR model. Now, the Capasso and Sirio, they have generalized the Kermack mechanistic epidemic model, and the generalization form is this: ds by dt in place of minus beta I, they have taken it is a function of gi, and this will go here in I population, and other terms are same. And where g is the continuous bounded function which takes into account the saturation phenomena, and these are the some condition based on that one. These are the requirement for G. And later on, the one of the statistician, MS Bartlett, in 1949, they gave the stochastic analog of the SIR model, and that also published in a very famous journal, Journal of Royal Statistical Society Series B. And later on, his students, the David George Kendall, who generalized the Kermack mechanistic model to a space-dependent integral differential equation. So this is the form of the model, Kermack model. This is the Kendall version of the well-known model. He has just replaced the I by this term, integral from minus infinity to infinity, I by t, and kxy is the kernel term. They have taken this one. And later on, in 2001, the one Japanese scientist, H. Inaba, he revisited the variable susceptibility model proposed by the Kermack and McKendrick in 1933, and they reformulated the variable infectivity model as a nonlinear age-dependent population dynamic model. And this is the form of the model, where this toy term is the disease age or infection age or class age. We assume this. And he found the existence, stability, and linear stability of that model. And he claimed that his model was the generalization of the very famous model, that is Pease evolutionary epidemic model during that period, 1987, that was published in Theoretical Population Biology. The Pease gave the model a evolutionary epidemic mechanism with application to type A influenza. So he says that his model is the generalization of this famous model, and he got the existence, uniqueness, and the linear stability of that model. Now, how to model with the data? So recently, many people have tried during the COVID period to model the data in the framework of the SIR model. So one of my students, he wrote the paper, SIR model assumption for the spread of COVID-19 in different community. He tested the data, taken the data from coronavirus worldometer, and taken the three population, the total infected class, and the infected individual, number of infected individual, and the dead individual. And they model in this way. And the initial adjusted the numerical simulation from the given data based on the Euler's method, first order Eulerian integral method, and solved it numerically, and took the initial infected population as the removed model. This I max divided by f is the factor, and I max d is the maximum number of infected individual, and these are the three parameters they have taken, beta, gamma, and delta, and solve it numerically with the steps like this, and during the 200 days, data with the 200 days, and they got this result for the Indian scenario. So they calculated the total infection, active infections, and the recovered population with this data set. And finally, they calculated the number of death and number of the susceptible population after certain days. So during 200 to this means from 14th March to 13th September 2020, and the data from the March to June 2020. So this is the outcome of that modeling from the data. And same thing, they have taken the effect of removal versus the death, and it is this is the this is the data point. And for modeling the death rate, they have taken the nonlinear function like this, d naught into e to the power 1 minus e to the power minus k rm, and rm minus d will give you the recovered population. And this is the nonlinear fitting. And for fitting there, they have used the trial and error method and calculated the number of deaths. So this is the, people are tried different way with the different data, whatever they observed, for setting in the modeling scenario of SIR model. Now let us come to the spatial role of the spatial model, how the spatial model affect the modeling scenario. So the basic principle for prevention and control of the infectious disease are the two basic principles. First, we have to eliminate the source of infection, and second, we have to cut off the route of transmission and protect the susceptible population. So for doing this, we have this spatial dynamics is also very important. So for modeling the spatial dynamics, these are the approaches: cellular automata theory, network theory, meta population theory, reaction diffusion equation, and integral differential equation. If you take the discrete time and continuous time, discrete space or continuous space, different type of model will emerge. If you take the continuous space with continuous time, you will get the reaction diffusion equation. If you take the continuous space with the discrete time, you will get the integral differential equation. If you take the discrete space with continuous time, you will get the meta population model. If you take the discrete space and discrete time, you will get cellular automata theory or coupled map lattice. In meta population work, you might be knowing Professor Ilkka Hansky. He is very famous from Finland. He wrote a very nice book on the meta population dynamics. So these are the many people are working their own perspectives with the data, with modeling, all these things. And this spatial dynamics for specifically for epidemic model, we can take these three category model: the diffusion based epidemic model or distributed contact model are formulated using the integral equation with the kernel. And third one is the restricted movement model, in which each individual has the home position about which individual move in the random walk. And let me show you some work review in that direction. A very nice article wrote by Relay et al. In 2015. They have highlighted the 5 open challenges for modeling the spatial epidemic model. And so that is a very good paper, very nice paper, highlighted all the problem faced by the modeler. And another work is done by Capasso in 1993. They have taken the spatial model in finite domain, stationary states, and study the stability of that model, global, local, all this stability. And spatial model with infinite domain, one can determine the traveling wave if it exists, minimum speed propagation, asymptotic speed of propagation, and determine the stability of the traveling wave solution. People have also tried stochastic spatial epidemic model. So let us see few model in the spatial domain. So this Capasso has developed the diffusive analog of Kermack mechanic model with the modification in the interaction term this way: A into A is a function of I, and this is spatial, X stands for space and T for time, spatial temporal in the bounded map. So this is the thing, and this is the no flux type boundary condition, and this is the initial condition. So they have fully analyzed the model, and they have taken gamma is the removal rate of the infective due to recovery or death of the epidemic people. So it is published in SAM journal, so you can go through that paper and find all the solution related with this. Another model is model with the vital dynamics. These people, Chinvi Sati and this in 2010, they studied the transmission of the whooping cough or measles epidemic, and the spatial version of that SIR model. They have taken the birth and death rate, both are equal, and no disease death in that model. The model is this, the standard version of the model is this, same beta minus beta SI, mu of n minus s. This is the alpha and beta, both are the diffusion coefficients are same for susceptible and infected population and recovered population also. And this is the Newman type boundary condition, and this is the initial condition. So with this framework, they have studied the spatial version of that model, and they have taken the total population is this. Since R has no role, so it converted into this model, and finally determine R by this way. They solve it for, it has two equilibrium point. One is disease-free equilibrium point, that is this, and other is endemic equilibrium point, and that is given by this one. And they have also find the prove that endemic equilibrium point is locally asymptotically stable, and it is also shown that it has globally asymptotic stability with the non-trivial initial condition. So these are the framework for proving the stability analysis. We have to find the characteristic equation, write the calculate the eigenvalue. If both the eigenvalues are negative, it shows the asymptotic stability. If one is positive, other is negative, it shows the saddle point. If both are positive, it shows the unstable situation. So these are the framework. Everybody knows that. Hope. And this is the simulation results by that people. They generated the space series with this set of data and different value of diffusion rate alpha. So for alpha equal to 0.001, they got this one, and almost same. And as we increase the diffusion coefficients, they perform this type of dynamics. This and calculate corresponding the surface plot is given by this one. And they have taken the initial condition is like this, and the final result shown by the numerical simulation is the dynamics of the whooping cough depends on both diffusion rate and the contact rate, and they have suggested that reducing the contact rate for susceptible human is good policy in order to control the whooping cough. And if the contact rate is large, whooping cough may becomes the pandemic. So this dynamics of whooping cough depends on both contract and the diffusion rate. So we have to, for dealing with this, we have to take care of the contact rate as well as the diffusion rate. Another model, Wang and Ruan, they have incorporated the treatment rate in that and studied the bifurcation, including the saddle node bifurcation, Hop bifurcation, and homoclinic bifurcation. In the SIR model, SIR setup, they have included the treatment rate. And in that model, later stage, Liu and Jean, they have studied the spatial version of that model, and they calculated the different type of pattern in 2 dimensions, and they found that they are showing the labyrinth spatial pattern in that model. So this is the form of the model. A is the constant recruitment rate, D is the just death rate, and this is the transmission rate by this way. This added here, this is this, and HI is the treatment rate. This is added here also. This gamma I added here, recovery rate, and D death rate for all. They have taken same minus DS minus DI minus DR. This DS, DI, DR are the diffusion coefficients. So many people have taken different type of treatment rate. Someone has taken constant treatment rate. Someone is taken depending upon I. This for. So this removal rate of the infected population due to the treatment one. And in different form of HI, they increased the complexity of the model and calculated the dynamics at going close to the reality. And this is the analysis performed in that model. And they also calculated the Turing space, and for testing the Turing pattern, we should have to have these 4 inequalities satisfied. And this if you plot this HK square versus K square, if this comes, this confirms that it supports the Turing phenomena, and this shows that this part it has the unstable, and as we increase the diffusion, it becomes stable. So this is the role of the diffusion. If you increase the diffusion, the system becomes stable. So it is justified by this simulation results. Later in 2015, Professor Dubey have also studied the SIR model in nonlinear incidence rate and the treatment rate. And this is the model. And what we did, we added the diffusion in that model. In the model considered by Professor Dubey, we have added the diffusion and studied this and taken the treatment rate as this one. And we calculated the basic reproduction number. This comes out to be this. And this shows that if R not equal to 1, solution converges to transcritical bifurcation. If it is less than 1, the disease-free equilibrium is locally asymptotically stable. If it is greater than 1, it is a saddle point. And after solving this, we got the endemic equilibrium point E1, S1, I1, where S1 is this, and this E1 is locally asymptotically stable, globally asymptotically stable, and saddle point, and it exhibits the Hopf bifurcation. And in the diffusion model, this is the scenario. But this given set of parameter value, we got the Turing pattern, and these are the Turing pattern for different iteration number. Initially, it shows this at 300, at 600, this is 900, at 5,000. At the population, this density increases, and this is for the susceptible population. So it shows that system becomes stable or disease-free as we increase the iteration number. So later on, Lee et al. In 2017, they taken the saturated treatment and logistic growth rate in SIR model and used the bilinear incident rate, and they proposed this model. The logistic growth rate and others are same as previous cases, and HI is this, and they used the bifurcation theory and got the so that this system exhibit backward bifurcation, Hopf bifurcation, and Magneto BT bifurcation. And to eradicate the disease, it raises the efficiency and enlarge the capacity of the treatment. They suggested that one. And later on in 2011, Yang et al., they have studied the existence of traveling wave in SIR epidemic model with the nonlinear incidence rate. So this is the model with the delay and diffusion. Both they have taken. Here no flux boundary condition, and this is the initial condition. Initial condition also depends upon X as well as T, and in that, and taken the delay time, this one, and by using the cross iterative method and Sauder fixed point theorem, the problem of existence of traveling wave they have established, and also it reduces to the existence of pair of upper lower solutions. They have constructed the pair of upper lower solution to the general form and established the existence of the traveling wave solution, and that traveling wave from the disease-free equilibrium to the endemic equilibrium state. And this shows the traveling wave solution for different value of the delay term. When you take tau equal to delay time 0.2, it shows this. If we increase the delay time 0.2 to 2, we get this type of the traveling wave. So from this model, it has been established that all the SIR model, different form of SIR model we have seen, delay, diffusion, temporal, all these things. So these are the. Let us go to the next section, that is how to model the non-local epidemic model and how to incorporate the age, space, quarantine, all these things. So we take the basic model from the susceptible, infected, and recovered population. Modeling scenario says that rate of change of susceptible population is nothing but mortality plus interaction. I dot is mortality per interaction. This. Now we want to incorporate the quarantine population in the SIR model. So where to incorporate? Infected population is classified into infective and quarantine, and other two are as it is, susceptible and recovered. Now the model becomes this way: S dot is same mortality interaction, I dot, Q dot, and R dot. we have I dot we incorporated with quarantine, without quarantine. So this is the things. Then we incorporate the quarantine with age structure. So S, I, Q, and R all are the function of time as well as age. And we have two independent variables. So the model, OD model becomes the PD model. So rate of change of del S by del T and rate of change of del S by with respect to age. All the population, we consider this. And the right hand side part is same. It contains motility as well as interaction. Now we use the space also. We have incorporated quarantine population and age structure. Now I want to include space also. So S becomes the function of T, A, H, X is space, all these things. And for modeling this individual movement, X have the role of movement. So for modeling this, we have to incorporate the velocity term. So we take the velocity of susceptible population, infected population, and recovered population. And we use the theory of crowd dynamics as we are using the crowd dynamics, how to model the velocity term. And so this becomes this. So we have added this divergence term of VSS, divergence term in VII. Quarantine population not allowed to move. So here we have not added, and recovered population is also allowed to move. So we have added the velocity term on the basis of crowd dynamics. Now we take the mortality term, non-local model with mortality. So we assume the mortality corresponding to that. So for susceptible population, mu is mu S, I mu I, Q mu Q, and R mu R. In most general case, we take same mu S, mu I, mu Q, and mu R as the same. Otherwise, it is dependent upon the population. So mu S is a function of also time, age, and X. It varies with time, age, and X. And now so this is the structure of the model for the mortality general model, including the time, age, space as the mortality of this. So nothing is left. Now we go for interaction. Interaction is left. Interaction is where to interact. S becomes infected. So it is negate minus in the susceptible population and added in the infected population. Now infected becomes quarantine. So taking negative term here and added here in quarantine population. I becomes recovered. It goes to recovered population, and quarantine becomes recovered. It added to the quarantine population. So this is the general hypothesis. Now, the first term is as it is. Just we have copied last form here. Now I want to take the delta. Delta as a rate of infective becomes quarantine. Epsilon is the rate infective becomes recovered, and gamma is the rate infective quarantine becomes recovered. So I to Q is delta I to R becomes epsilon R, and Q to R becomes gamma Q, quarantine individual. So we have added this. This is for I to Q is delta I to R epsilon I, and Q to R is this one. So we have marked with different color. So now I hope this is clear to everybody. Now we go to the interaction term, modeling the interaction term. Other term I have already modeled it. Interaction left with S to I. How to model this? So this is the beta. We have to incorporate the beta, the digit transmission rate. It is not in transmission probability. So in 2020, RM Colombo, they have taken this form of the interaction term. S to I is beta is also dependent upon time, A, space, and this one. And we have taken the discrete form of this. And I wrote a paper in nonlinear dynamics, age structure modeling. And in that age structure social contact, I have taken this S to I as a beta into weighted coefficient of contact of age class I to the entire population by this form. And this is given by the contact matrix, and this contact matrix is calculated by contact between household people, working people, school-going children, and other people. All these things are calculated. The involved in calculating the matrix. And what is the role of beta? We want to specify it here. So beta is just beta I. This is just taken as the interaction term. Beta I with S, beta I with S. Now we take the transmission, virus transmission. We assume the small distance epsilon, and that satisfy this norm of x minus epsilon. X minus zeta is greater than epsilon. This implies that the transmission becomes 0. Beta of this becomes 0, and where x and y are the specific position in the given domain x, where this epsilon represents the maximal distance at which the virus can transmit. It has the capacity, how long it will transmit. In case of epidemic, in case of pandemic, in both cases it is different. So we note that the speed of infection is infinite within the given distance, and dependence of beta is age and alpha, both considered for the specific age. So beta and delta is this. So beta is the digital transmission, delta is described as isolation of infected individual. So model becomes this one. And now we calculate the R naught for this model. R naught for non-local model. We have taken this formula from the May book. I visited University of Cambridge in 2012 when the whole England is celebrating the computing in the computability in Europe 2012 in the remembrance of the Alan Turing. At that conference, I met with Professor. He written 2 or 3 books of mathematical biology. In that book, they have given the formula for calculating R naught. R naught is nothing but average infection rate multiplied by the number of susceptible divided by the average recovery rate. And you will also find this formula in the very good book, The Epidemiology and the Control of Malaria, written by MacDonald in 1957. And we have calculated this R naught based on these 2 references. R naught comes out to be this, and we can take different classes: infective one, quarantine one, hospitalized one, different form. So depending upon this, we can calculate R naught is this, Q naught is this, and recently the Adam Chapsky, they have given this calculation. If R naught is greater than 1, then it goes number of infection, new infection goes up to this. At that point, you apply the control measure, then it start reducing. And if you change the control measure in different way, it behaving like this one. So this is the role of effect of R naught versus time, nicely presented by this one. So this R naught is less than 1, imply by d dt of this less than 0. If it is greater than 1, this is greater than 0. Same way, Q naught also behaves in the same way. Here, remark is for proving this, we can use the elementary application of the divergence theorem, and you will get the result. And another remark is R naught measures the danger of being infected, and Q naught measures the overall effect of the disease spread. And in that case, this will happen. Since we have less time, so I am skipping the vaccination strategy from here. Let me go for other part, how to model this. I'm just skipping the vaccination one. So let us. So I also did one in the beginning of the Corona period. I wrote a paper, the age group targeted testing for COVID-19 as a new prevention strategy. In that, we have taken the age structure multi-group model, and we divided the whole population into S, I, Q, and R, and we have also tracked the fatality rate. And this is the schematic diagram for this one. And we have taken the lambda I as this one. And I have also considered in the same model how to model for symptomatic and asymptomatic population. So this multi-group model, by incorporating the symptomatic and asymptomatic population, it converted into this, and lambda is same, and how to calculate the contact matrix, the same formula, and these are the just procedure how to calculate all these things. We have divided the whole population into 16 group, 0 to 5, 16 age group. So total we have 80 differential equation for the 5 group. Each group is 16. For S is 16, 0 to 5, 5 to 10, up to 80. And where the data for, and we have tested it for 3 countries, India, Italy, and USA. For USA, we have taken up to 0 to 75 years because data is not available. So, and we use the Python code NumPy for modeling these things. And this is the formula for calculating the R naught in the multi-group model. And these are the population available on the net, the data for susceptible population, which we used for our modeling. And this is for the mortality rate that is also required. And based on that, we have calculated the R naught, India, USA, and Italy, all these things. And in the beginning of that one. And this is the, just we use the protected version of that, all the 3 countries. So we have calculated the infected, quarantine, and the total infected population. And here is the, we have fixed the testing on the 5th May, around that one, and it shows the, it is decreasing. And for the Italy, it shows it start decreasing very after the 30th May, all these things. So these are the some result based on that one. And we have taken the for all the 3 countries, which groups we should test first, because India is a big country. We have 1.3 billion population, so it is not possible to test all the test or vaccinate all the population at a time. So we give the guidelines to whom to test, whom to vaccinate first. So those who are the more vulnerable stage, we have to test them first. So we got that 15 to 45 age, they are the most exposed classes. So we suggested that we can go for testing for these group only. So this is valid for all the 3 countries. And we have also seen that government has also adopted something like that policy. We have to vaccinate more than 60 years age, then more than 18 years age, then now they have started 12 years and more, all these things. This is Colombo has also calculated the infected population between this different age group, 0 to 40, 40 to 60. So this got the total infected population, and this is all these things. So its result is also matching with our result, which we calculated for the discrete data set. And this is the model data, and this is the real data, and it is almost matching on this thing. In case of Italy, it is decreasing much earlier of that. So these are the results. So age of 15 to 40 years, most likely to catch the infection. So we should first isolate these people and restrict their disease transmission, all these things. And these are the targeted testing. After testing, if you adopt the not random testing, targeted testing, and then we calculated the infected, quarantine, and total infected, it has significant impact on that testing. This dotted line will show you the reduced rate of that one. And this is the just Indian basic reproduction number before targeted testing and after targeted testing. After targeted testing, it reduces and comes below 1. So it has significant impact of this one. So testing you can replace by the vaccination. After targeted testing, you vaccinate them, isolate them, quarantine them, and you will get the proper result. It has some impact on that one. So this is the showing the calculation of R naught number, because R naught is very important. And these are the some result related with this one. So India has observed the comparatively lower mortality rate, and as we the mean Indian, why it is so lower mortality rate? It is due to most of the population in Indian population is younger, and the mean age of Indian population is 26.8 years compared to USA 38.2 years and Italy 45.8 years. So we have also some limitation of this model. The choice of single transmission coefficient beta across all the age is because of the lack of age specific data or transmission dynamics. We don't have the data for different age group how it is transmitting. Now let me show you the model with comorbidity. So this is the real story. It happens in my family. He is my relative. He is 62 years old and his mother is 80 years old. Both in the second wave admitted in Delhi, and he has some disease, suffering from some disease. So he could not return it, but his mother is well. She got 2 times infected, but she returned to the home and now she is well and leading her life, but he could not make it. So in case of corona, comorbidity has major impact. So we have tried to model this scenario, comorbidity case, and we published the paper with controlling the non-pharmaceutical invention and vaccination policy. We have formulated the model. And we did the qualitative and quantitative analysis, and it follows the number of COVID cases follow decreasing and increasing trend. So we apply the entropy. Entropy leads to the explaining the heterogeneity in diffusion and the force of infection. And the trend of force of infection is investigated by Shannon entropy that is used for spread of pandemic, and other entropy is used for just for testing it has the pandemic or not, and it follows the Boltzmann classical thermodynamics. So this is the model. So we have taken the susceptible population, exposed population with and without comorbidity, infected without comorbidity, with comorbidity, and recovered population. And this pi s is the average recruitment rate, beta s is the transmission rate, 1 by mu is the average life expectancy, and all these things are well known to all. So this is the model, and this epsilon is important. Epsilon is the fraction of exposed individual without comorbidity, and 1 minus epsilon is with comorbidity. So this is the complete model is like this, with initial condition this, and we have analyzed the qualitative analysis, and this is the quantitative analysis, curve fitting with the data. Data is recorded in the Indian case, and fitted on this curve, and it is well suited. It is the confirmed death cases, the data, and it is just following the trend, same trend. And this is in case R naught is 1.0607. We have also tested the sensitivity analysis by following this work, Marino et al. And we performed the uncertainty analysis by using the algorithm LHS method and sensitivity ERCC method. And this is the effect of variation of R naught we have calculated. And we find that only increasing value of beta s, this is beta s, that can shift from R naught less than 1 to R naught greater than 1. And as we increase the value of R naught, it increases like this one. In second and third paper, it effect on the recovery from the infected population, recovered from the comorbidity, without comorbidity, with comorbidity. And this is the bifurcation analysis, and it shows that the occurrence of forward bifurcation that indicates that disease persists, and as population, susceptible population must aware of the disease spreading, and the region of the curve is smaller to reduce the infection. And like the value of, if you change this xi is the fraction that without comorbidity, if we increase that, it increases, stable region is increasing. And this shows that 7-day trend of the death rate. 7-day moving average we have calculated, and this follow the modeling by nonlinear function by this way. And if we study the effect of infection, so this is we assume this term as a force of infection, and this is the average of that one, force of infection. And in case of the beta S, it shows the increasing trend. It shows the force of infection is increasing. And in case of gamma I and gamma C, it is the decreasing trend. And same we have calculated for this one, the data, quartile 1, quartile 3, all this numerical requirement, and we have given the value here. As per this value, we have calculated this box diagram. And this is the pattern gamma I versus beta S, gamma C versus beta S. This is without infected, without comorbidity, with comorbidity, and it shows the expected value is of the force of infection is entropy is this one increasing, this two is decreasing, and this is the combined dependence of gamma I versus beta S and gamma C versus beta S. So entropy within the force of infection, it measures the disorder due to non-uniform distribution of the disease spread, and we have used the Shannon entropy for calculate this value H by using this formula, and where Ni represents the events with length eta I, and P of Ni is nothing but the probability of the event that occurs based on the frequency of non-recurrent based model. And if we compare the previous 6, this figure, this with 7, 6 with this 8, both have the same trend. So both are positively correlated. And if you compare 7 with 8, we will find that both are alike pattern and enhancing the entropy eta as well as E of eta. So this assess the dynamically disordered state for the force of infection in the parameter space, and we do the optimal control also for that model. So these are some conclusion based on model with comorbidity. From ecological perspective, comorbidity individual gets gradually infected due to lack of precaution and prevalence. So like this, so S becomes I, it turns into E and prevent the COVID. The study of transmission, average fluctuation, force of infection, all these things can be calculated, combined effect has calculated, and we have used the Shannon entropy. It shows more disorder in average value of this force of infection. It shows the optimal control strategy shown in the combined effect of non-pharmaceutical events and vaccination effects. It has much effect on the minimizing the COVID-19 and its social and economic cost both. The proposed strategy is fruitful for our society. Well, people have also studied the genome epidemic. So for complete view of epidemiology, we should also, one part, this deterministic epidemic model is not sufficient. We have to go for genome epidemic also. So I have just calculated some literature, gone through this. So people have studied this genome epidemiology, and they have taken the different genome sequences and calculated this data, genome sequence for SARS-CoV-2, and having some idea about this. And both knowledge is required for complete eradication of the epidemic disease. And recently in chemistry 2020, these two ladies got the Nobel Prize for advancement of a method for genome editing, and that is used for DNA of microbes with high precision. And so what are the challenges? Challenges is how to utilize the genetic as well as spatiotemporal epidemiological data together to predict the onset and spread of the outbreak. And it provides the government and healthcare agency the critical information to control the outbreak. So the future work will be how to integrate the genome modeling with the spatiotemporal epidemic modeling, and also add the non-local diffusion to our model to examine the spatio-temporal pattern of this pandemic. And there are few cases where we do not have the model right now. So in that case, where the immune response of virus and pathophysiology of the virus disease remains outside the modeling effort because of complexity of the phenomena. Modeling of blood coagulations include clot formation in flow taking into account the biochemical reaction of plasma, platelets aggregation, the active area of research. So the one possibility is its application in the clinical medicine is remain limited. The main difficulty is here related with the large variability of patient-dependent parameters of the model, numerous reaction rate constant of the coagulation reaction in the plasma cannot be easily determined the individual patient because of time and cost constraint. So these are the situation we do not have the model. So my final message, I give you the with positive notes. So let us consider the ecological concern of the pandemic from all over the world are quite exhilarating and encouraging, which the poets received as a silver lining. It provides a stage and speech for nature to heal it. Water, air, river, forests, ocean, all got relatively purified. And birds, animal, insects appears on the road, striking a balance in the ecosystem during this epidemic period we have seen in corona period. And the peacock, flamingo, deer, leopard were seen roaming freely on the lonely highway of the road. And many people recall the perceived change as the return to the nature. And I have taken this picture from the Instagram. One guy, Mano Maglani, he uploaded in. This is the peacock found on the car during the corona period. And this is the rare event from the Bombay. This is the rare event in the hustle and bustle of the city. During the normal day, it will not happen. So they observed this. And this picture shows the joy of the Gangetic, this animal, which found in the Ganga river in Bihar somewhere. So these two events only possible during that period only. And these people say that the return of this after 30 years, people have observed in the Ganga. So with this message, this magnanimous spirit of nature was beautifully captured by the poets and writers in the romantic spirit. And one of the author, Anu Majumdar, she is the editor of one of the poetic literature. The name of the Sahitya literature is Hibiscus. She wrote nicely about this event. Earth are taking us all to court, questioning us with its beauty, the quality of our air, the evidence in our breath, our life, our ambitions, our death, our faith, and how we heal all of this in the justice that will empower the world. So this is cited from the Sahitya Setu literature of the journal. So with this, let me stop my talk. This is my group who is working with me, and let us have thanks to all. And now the session is open for question. If you have any question, you can ask. Let me.
Thank you so much, Professor Upadhyay. It was a very nice and excellent